So a quick review of reciprocal trig functions. What did we do? We graphed the bottom function first. Then the first thing we did was put in all of our asymptotes, followed by nice points, and then we graphed it showing the asymptotic behavior. So we're going to do the same thing with cosecant, secant, and cotangent, and we're going to find out that cotangent has a little special case involved in it. So I'll show you what that means. But first of all, right, and those we all. First of all, the graph of sine is given. So we start with our asymptotes, and we're going to have asymptotes wherever we have x-intercepts. So we have an asymptote there. That one's a little, I'll just try the best as I can to make it go through in the right spot. There we go. And we can label all of these. Since we know the zeros of sine, we can label these x equals negative pi, negative 4 pi, x equals negative 3 pi, x equals negative 2 pi, x equals negative pi, x equals 0, pi, 2 pi, pi, and 4 pi. Will we have a horizontal asymptote? Remember, we have a horizontal asymptote when our original function's y values get really, really big or really, really small. But in this case, they don't. The biggest your y values get is 1. The smallest your y values get is negative 1. So there's no horizontal asymptote. Step 2, nice points. What are some nice points that you know on sine? Well, you know the point pi over 2 comma 1. There'll be another point comma 1 here. We have 3 pi over 2 comma negative 1. And so in fact, all of these points where sine of x is equal to 1 or equal to negative 1 will all be nice points. If you wanted to do another nice point, you could. Since you know on your original graph here, for example, what's sine of pi over 6? Ooh, do we have to study our pi plate a lot for the exam too? Yes. Sine of pi over 6 is 1/2. So what will the reciprocal be? One over 1/2 is just the reciprocal, which will become 2. Now you wouldn't have needed that point, because with the points that we have, and knowing that reciprocal graphs do not have any x-intercepts, you would know the only way you could show your asymptotic behavior in this section would be to go up, and in this section would be to go down. And so we can complete each of these sections and the black graph is the graph of cosecant. I would like you to do the graph of secant on the next page on your own. Let's see how you did. So, first of all, you would have started with asymptotes wherever you have x-intercepts. And labeling them, well, we have x equals pi over 2, x equals 3 pi over 2, x equals 5 pi over 2, x equals 7 pi over 2, and the same thing in the negative direction. With the secant graph, we also don't have a horizontal asymptote. Nice points. You'd have 0, 1, 2 pi, 1, negative 2 pi, 1, negative 4 pi, 1, negative 3 pi, negative 1, negative pi, negative 1, pi, negative 1. And since a reciprocal graph has no x-intercepts, we know that when graphing the asymptotic behavior, some sections will have to go up and the other sections will have to go down. And we notice that the secant graph is the same shape as the cosecant graph. They're just horizontal translations of each other. The last one that we're going to look at is the cotangent graph. And cotangent is a 1 over tan graph. But I also want to write up here, just as a reminder, that cotangent is also cos theta over sine theta. So the graph of tan is given, and we're going to graph the reciprocal of tan. And we're going to notice that with the cotangent graph, there is one special case that occurs. And I'll show you that in a second. We can start with our asymptotes. First of all, we will have vertical asymptotes wherever we have x-intercepts. So we can draw those in. And we can label them, and you'll notice that your asymptotes are at the exact same places where sine of theta is equal to 0. So we have an asymptote at x equals 0, x equals pi, x equals 2 pi, x equals 3 pi, x equals 4 pi, and similarly going backwards, negative pi, negative 2 pi, negative 3 pi, and negative 4 pi. Now with the horizontal asymptote, this is where cotangent has an exception. And the exception is as follows. Normally, when your original graph, such as tan, goes up forever or down forever, you would have a horizontal asymptote at y equals 0. That's how we do all reciprocal graphs. With the graph of cotangent, it's a little bit different because a decision had to be made. Are we going to graph cotangent as equal to 1 over tan? And if you graph cotangent equal to 1 over tan, you would have an asymptote at y equals 0. But if you graph cotangent as cos over sine, you do not. For example, if I give you the value of pi over 2, take out your calculator or use your pi plate. Plug pi over 2 into 1 over tan of theta and see what you get. Plug pi over 2 into cos of theta divided by sine of theta and see what you get. So either use your unit circle or use your calculator and tell me what happens when you do 1 over tan of pi over 2, and tell me what you get when you do cos of pi over 2 divided by sine of pi over 2. Has anyone done the 1 over tan of pi over 2 already? No? Anyone done the cos of pi over 2 over sine of pi over 2 already? Okay, once someone gets either of those, let me know. This one's an error. Yes, this one is undefined. Because tan of pi over 2 is undefined, that doesn't exist. And that's why if you graph this 1 over tan of theta, you would get an asymptote at y equals 0. But what happens when you do cos of pi over 2 over sine of pi over 2? You get 0. So depending on which idea of cotangent you're going to use, it's either undefined or 0. And it is decided to use the cos over sine, so wherever there were asymptotes, those will all be 0. And that is the exception for cotangent. Now, if we look at other nice points, what's a point on tan that you know? That's nice. You know the point tan of pi over 4 is 1. What's going to happen to that on cotangent when you do the reciprocal? It's going to stay the same. In fact, wherever your y values are equal to 1, because 1 over 1 is 1, all of those points are going to stay the same. Another nice value you know, (3 pi over 4), tan of 3 pi over 4 is negative 1. What does that mean for cotangent? Well, you'll have 3 pi over 4 comma 1 over negative 1. That point won't change. In fact, every point where the y value is negative 1 is going to stay the same. And now we have enough points to draw our graph towards the asymptotic behavior, towards the asymptotes with the asymptotic behavior. And the cotangent graph looks like an x cubed graph that has been flipped over the y-axis, a whole bunch of them. Hopefully you were able to color code things in your notes. If you were using pencil through the whole thing, your page might just look like a bunch of pencil. Question?
So is it basically just like moving over a bit, like moving
Well, the asymptotes are getting moved over wherever you had x-intercepts for tan. And then wherever y was 1 or y was negative 1, those points didn't change. It's not a translation over because now your curves are going down, right? And like they're curving the different way. Yes? We don't have a horizontal asymptote because for cotangent, it's decided that at pi over 2 it exists. They're using this. We were using 1 over tan to graph it, but for the values, cotangent over sine is used. And it works for everything in tan except at pi over 2. So normally, yes, with a reciprocal graph, in this situation, we should have a horizontal asymptote. And so cotangent is the exception because the graph of cotangent technically is this. Cotangent, they're saying cotangent does exist at pi over 2. Where normally if you were doing the reciprocal graph of tan, since tan doesn't exist at pi over 2, therefore cotangent shouldn't exist at pi over 2. But it's decided that we'll use cotangent as cos over sine for all of its values. So we'll say cotangent does exist at pi over 2. And for some of you who are working on your exam review, now you can do question number 10 or 12, asked to graph cotangent. So now you're able to graph cotangent.